So welcome back to the deep dive. Today, we're jumping into something that feels, well, incredibly solid, but also really quite subtle. What is mathematical knowledge?
Yeah, it's funny, isn't it? You have these truths that seem completely unshakable, universal even.
Exactly. But then you realize, hang on, this is something humans do, something we've built up over time across different places.
Right, so that's the big question we want to wrestle with today. Is math something we, find out there, like discovering a new continent?
Or is it more like something we build, like inventing a game with its own rules?
That's the core tension, yeah. You get these results, they just feel true, almost eternal, but the deeper you dig.
The more you see the human fingerprint, the
Yeah.
choices, the history.
Precisely. So our mission, if you like, for this deep dive is to unpack that seeming contradiction, what really shapes what we call mathematical truth. Have you ever stopped to think, is 2 plus 2 4 discovered or invented?
It seems so obvious, right? Let's start there, with that feeling of timelessness. You
Yeah.
mentioned Euclid,
Oh, yeah, Euclid's Elements, written, what, 300 BC?
something like that. And his theorems, like the Pythagorean theorem, they're still just as true today. It was apparently the math textbook for ages.
For centuries, yeah. And it's not just complex geometry. Like you said, basic arithmetic, 2 plus 2 equals 4. That feels like it has to be true, doesn't it, for anyone, anywhere?
You definitely get that impression. Mathematicians sometimes talk about it like they're, I don't know, charting an abstract realm, finding these eternal truths.
It's a powerful image. But here's the twist. That feeling of pure objectivity, it's actually built on, well, choices. Agreements we've made as a community.
Agreements. How so? Like voting on theorems.
Not quite like voting. But think about something like, okay, 0.99999 recurring equals $1.
Right. That one always felt a bit weird.
Well, Keith Devlin makes this point. We accept it as true because of earlier decisions mathematicians made about the foundational rules, the axioms.
Axioms. Those are like the starting assumptions, the
Yeah.
ground rules.
Exactly. The fundamental rules of the game for a particular mathematical system. And the truth of any statement, really, hinges on which set of rules you've agreed to play by. We define things.
And then logically see what follows from those definitions.
Spot on. You define your terms, you set your axioms, and then using rigorous logic, you arrive at theorems that are true within that system.
So it's like we choose the setup, the initial rules,
Yeah.
and the results are then locked in by logic. But the setup itself, that was our call.
Precisely. It's the consistency inside that framework, the rigor, that gives math its special kind of objectivity. If we agree on the axioms, we have to agree on the theorems that follow logically.
Which is why maybe two pebbles and two pebbles always seems to make four pebbles no matter who's counting.
Yeah, that empirical feeling reinforces it. But the mathematical truth of $2 plus 2,444 Hall rests on that axiomatic foundation.
It's that classic discover versus invent question again, isn't it? It feels like it's somehow both.
It really does. A paradoxical, yes, it's both. You feel like you're uncovering something real objective.
Like Einstein being amazed that math works so well for physics.
Right. But it's all built on these frameworks we constructed. And even that objectivity has cracks, or maybe limits is a better word.
Limits. What do you mean?
Well, Kurt Gödel, his incompleteness theorems from the 1930s were revolutionary.
Oh, yeah, I've heard of those. They're pretty heavy stuff, right?
They are. Basically, Gödel showed that for any consistent axiomatic system that's strong enough to include basic arithmetic, there will always be true statements within that system that you actually can't prove using the system's own rules.
Wait, hang on. So there are mathematical truths that are true,
Yeah.
but we can't actually prove them using the very math system we set up.
Within that specific system, yes, it's a real mind bender. It suggests the whole landscape of math isn't fixed. It can grow, expand.
By adding new rules.
Potentially, yeah. Or by choosing different starting points. Think about non-Euclidean geometry.
Like geometry on a curved surface instead of a flat plane.
Exactly. Different axioms, different truths. So a specific theorem, once proved in its system, feels timeless. But the overall domain of mathematics, that's actually shaped by human choices and can evolve.
Okay, so the timeless feeling comes from sticking to one set of rules, one system.
Pretty much. Fix the axioms and definitions, and the truths follow logically.
But the axioms themselves,
Yeah.
we chose those. So $2 plus 2 plus 204 feels certain when I count chairs.
Empirically certain, yeah.
But its mathematical certainty comes from the logic, plus the fact that we all basically agreed on the starting rules for arithmetic.
It's that blend of logical deduction and, crucially, communal agreement.
Communal agreement. That brings us to the people involved, right?
Yeah.
Individuals and the wider math community.
Absolutely key. Math doesn't just happen in a vacuum. It moves forward through individual insights, sure, but those insights need to be,
Yeah.
well, checked and accepted by everyone else.
Right. You have these huge figures. Euclid, you mentioned, pulling together Greek math. Or Hilbert.
David Hilbert, yeah. His list of 23 problems in 1900 basically shaped a lot of 20th century math research.
And then you get these incredible, almost out-of-the-blue contributions like Ramanujan.
Srinivasa Ramanujan, amazing story, self-taught genius in India, producing thousands of results in number theory, series, things nobody had seen before.
Didn't his collaborator, Hardy, say some of the theorems just had to be true because no one would have the imagination to invent them?
Something like that, yeah.
Yeah.
The sheer novelty was astounding. And think of Emmy Noether, too.
Her work in abstract algebra.
Transformative. She basically redefined chunks of algebra. And her theorem connecting symmetries in physics to conservation laws. Hugely important.
So these individuals clearly steer the ship, creatively speaking.
Undeniably. Their creativity and deep insights push the boundaries. But, and this is the crucial bit, those insights don't just become math automatically.
They need the stamp of approval from the community.
Exactly. Validation is critical. A theorem only really gets cemented as knowledge after it's been rigorously picked apart, checked, and agreed upon by other mathematicians.
Andrew Wiles and Fermat's last theorem is the classic example, isn't it?
Perfect example. He announces this massive proof.
Huge fanfare.
Then a gap is found, and it took him, what, another year? Working with Richard Taylor to fix it? Only then, after that intense scrutiny and correction, did the community accept it.
It shows that even for groundbreaking stuff, that peer confirmation is non-negotiable.
Totally. Or consider the four-color theorem.
The map coloring problem,
Really?
needing only 4 colors.
That's the one of the first big theorems proved using a computer for parts of the calculation.
And people were uneasy about that.
Very uneasy initially, because no human could check every step of the computer's work by hand. It felt different. It took more time, independent checks, eventually a simpler proof structure, before it felt fully accepted.
So it really highlights that social dimension. A proof isn't just logic, it's convincing your peers.
Yeah, someone described proof as a social act of accepting it, or an explanation accepted by a given community at a given time.
And didn't Thurston say mathematical knowledge lives in the minds and social interactions of the community?
He did. It suggests that when mathematicians look at a proof, they're checking the logic, yes, but also, does it fit? Does it align with our standards, our existing knowledge?
So informal chats, intuition might start things off.
But it needs that formal write-up, the peer review, the long-term checking of published work. That whole communal process is what gives math its solidity.
Okay, so individuals have the breakthroughs, but the community acts as the gatekeeper, setting the standards for rigor and deciding what gets added to the collective knowledge base.
You got it. The flash of insight meets the collective agreement.
Which then brings in the idea of where and when did these ideas even come from? The cultural and historical context.
Right, because math didn't just appear fully formed, it grew within cultures.
You mentioned basic counting earlier. The idea of number itself seems to have popped up independently in lots of places, right? When people needed to track things.
Exactly. Devlin traces basic arithmetic way back, Sumerians, thousands of years ago. Wherever people counted, it started to emerge.
And then you see these different streams developing. India, for example.
Huge contributions. Brahmagupta, 6th century, getting a real handle on zero and negative numbers, treating them rigorously.
And the Middle East.
Al-Khwarizmi, 9th century Baghdad. His work is where we get the word algebra. And his ideas traveled, eventually reaching Europe through people like Fibonacci centuries later.
So what we think of as Western mathematics is actually this blend, this accumulation from different civilizations.
Devlin's point, yeah, at least 3 major streams feeding into it. And you can see how the needs of a culture shape the math.
Like needing math for astronomy or for trade or building things.
Precisely. Leading to different emphases, think Babylonian base 60 for time and angles, or Chinese traditions focusing more on algorithms.
So the knowledge itself, it's partly wrapped up in the culture that produced it, including the symbols we use, the methods.
Definitely. Our whole decimal system, with place value and zero that has specific Indian and Arabic roots, the Greek emphasis on proof, that's a specific cultural value too. How math is taught, that's cultural.
It's funny, Devlin notes that mathematicians in Western universities often feel math is culture-free.
But his observation is, well, they're just inside that culture, so it seems universal to them.
Like a fish not noticing the water.
Pretty much. And it's like any area of knowledge, really. Science has its paradigm shifts, its historical contexts. The human sciences are obviously culture-bound. Arts, religion, they all develop within traditions.
And even within math itself, you see traces of this history.
Absolutely. Non-Euclidean geometry challenging Euclid's assumptions. Different schools of logic, like intuitionism, questioning classical approaches. These weren't random. They arose in specific intellectual moments.
So while algebra might study universal structures,
The practice of math, who does it, how, why, that's shaped by history and culture.
it's got a lineage like any other field. It's not floating free of history. The way we accept a physics law or a math theorem both involve these societal historical processes.
Exactly. Which loops back again to the human element, even on a personal level. Intuition, personal experience.
Mhm.
How do they fit into this abstract world?
Yeah, it seems counterintuitive, but you hear about it all the time. Mathematicians talk about creativity, insights, hunches, seeing the answer before they can prove it.
Poincaré's idea of the two cognitive styles comes to mind again. The logicians, step by step.
And the geometers making these intuitive leaps, seeing the whole picture.
Right. He gave that example of Felix Klein using an analogy, something about electricity flow, to understand a complex math problem. It gave Klein this moral certainty, Poincaré called it. Totally different from just grinding through logic.
And doesn't our first encounter with math often come through experience? Like kids learning to count with blocks?
Absolutely. That concrete empirical grounding is often the start. 2 blocks and 2 blocks make 4 blocks. You see it, you touch it.
And then later you move to the abstract symbols, the proofs, like understanding why DPIP 999 nulls equals $1. But the foundation was maybe more hands-on.
And your background, your culture, can shape how you think mathematically, too. Ramanujan again.
His spiritual visions feeding his math.
He claimed they did. His whole non-Western background led to this incredibly intuitive, almost mystical style, at least initially. It shows how personal perspectives can influence the path of discovery.
Modern mathematicians also talk about that feeling of discovery,
Yeah,
right?
yeah.
Like they've stumbled onto something real.
Yeah, that subjective experience is powerful. Seeing a pattern hold in lots of examples can create a strong belief, a conviction, long before proof emerges.
But at the end of the day, math demands the proof.
Always. The intuition, the personal insight, that's often the crucial first step for new knowledge. But it's the proof that makes it objective, accepted knowledge.
It shows how those personal ways of knowing really do feed into even the most formal disciplines.
Definitely. Which leads to a final interesting comparison. How does progress in math stack up against other fields? Is it, like, harder to make progress in math?
That's a tough one. How do we measure progress? Is it proving new stuff? Solving old problems?
I guess so. Proving new theorems, finding counterexamples to conjectures.
On one side, math seems to build relentlessly. A proof, once accepted, is solid.
Yeah.
It adds to the structure. We don't really throw out old math like we might overhaul old scientific theories.
Right. Euclid's geometry is still valid within its own axiomatic system. It wasn't wrong, just not the only possibility. Proven truths seem permanent. That sounds like steady progress.
Yeah, but then you look at the really big, deep problems, the Hilbert's list, the Millennium Prize
These are
problem.
mostly unsolved, some for over a century.
Exactly. So progress on the frontiers can seem incredibly slow, almost glacial sometimes. Maybe harder than in science, where a new instrument might suddenly open things up.
Possibly. The nature of mathematical proof, that demand for absolute certainty, might make it inherently tougher than finding strong evidence or building a predictive model in science.
And compared to, say, the arts, where progress means new styles, or ethics, where norms evolve, math seems to measure progress by cracking these specific hard problems or building new theories.
Yeah, the benchmark is different, and arguably higher because of the proof requirement. A scientific theory might be the best we have for now, but it could be overturned. A correct mathematical proof, that's supposed to be forever.
Though both fields have brutally hard problems at the cutting edge, proving the Riemann hypothesis versus, understanding consciousness, both seem monumental.
Absolutely. So harder is maybe subjective, but mathematical breakthroughs often seem to need these radical new ideas, these conceptual leaps.
Like Galois inventing group theory to solve polynomial equations, or Wiles needing techniques from elliptic curves for Fermat.
Exactly. So math needs creativity, just like other fields. But it also needs that final, rigorous, formal proof for the progress to count. That double hurdle innovation and verification probably gives it a different rhythm compared to empirical fields.
Okay, so wrapping this up, where do we land?
For me, the big takeaway is just how multifaceted mathematics is. It's this amazing mix, universal logic, yet shaped by human hands and history. Objective structures built on chosen foundations.
Yeah, those truths feel timeless, but the systems they belong to and the way we found them are products of human culture and decisions over centuries.
And you can't separate the individual genius from the collective validation. Both are essential for math to advance. That brilliant insight needs the community's rigorous check.
And even personal intuition, that gut feeling, has a place in sparking discovery, even if proof is the final word.
It really brings home that classic tension we see in knowledge, generally certainty versus creativity, the objective versus the context-bound. Math gains its incredible certainty through our acceptance of its logical rules and processes.
So a final thought maybe for our listeners. Given this complex picture, the human choices, the cultural influences, the role of intuition, alongside logic, how does understanding the process behind math change how we think about mathematical truth itself?
That's the question to chew on. Does seeing the making of affect our view of the final product? It definitely makes you think about what knowledge really is.